Hello everyone and welcome to this video. So this is the video for CE 108 Mechanics of Deformable Solids, and I am Matthew Bauchi from UCLA. If you need to contact me regarding this class, my email address is Bauchi, like my last name, at ucla.edu. And so if you have specific questions about this class, and if you are actually enrolled in this class, then the most efficient way to ask a question and to get an answer as fast as possible is actually not to send me an email, but actually to use the Piazza platform to post your questions. So in this first video, what we are going to do today is to talk a little bit about what this class is about. We're going to see what is going to be the scope of this class, and trying to define a little bit what is actually the mechanics of deformable solids, what is this course about, and how it differs from the different classes in mechanics that you have enrolled in the past, like statics or dynamics. And we are going to see what are the different chapters that we are going to talk about during this quarter. So what is this class about? So this class is about the mechanics of deformable solids. So to understand what this class is about and what we are going to talk about and try to understand during this quarter, it's useful to define the terms behind the name of this class. So the first thing is mechanics. So of course this is a mechanics class, but you have already enrolled probably in several mechanics class. So the first question is, what is mechanics? How do we define mechanics? So the way we can define mechanics is we can define it as the description of the behavior of materials. So the mechanics describe the behavior of materials, but not all types of behaviors. The behaviors of materials that are induced by external forces. So it describes the behavior of materials that are subjected to some external forces, to some forces that are applied by something that belongs to the rest of the universe, something that doesn't belong to the material itself. So an external forces, which can be applied by an external agent or by applied to another material that is in contact with these materials. And if you have a force that is applied to a material, then this material is going to exhibit certain types of behaviors. And the different types of behaviors that this material can exhibit will pretty much define the different branches of mechanics. So the first thing that you have seen already during the previous quarter, most likely, is that if you have different forces that are applied to a given material, and this material is at equilibrium, then the first thing that we can describe is what defines the equilibrium of these materials and how the forces will balance each other. For example, if you have a material that is placed on a table, and if you apply a force on these materials, it means that the table, if the material is at equilibrium, the table will also apply a resistance force on this material that will be opposed to the force that you are applying to this material. So the force must be balanced. That's what you saw in the statics class. So this statics class is pretty much the fact that the sum of the forces and the sum of the moment must be zero if the material is at equilibrium. So that is statics. The second thing is, if you apply some forces on the material and this material is not at equilibrium, then the second type of behavior that will be exhibited by this material is actually a motion. So that's the second thing that a material can exhibit. If you apply a force, this material can actually move. And so this is what we talk about in the dynamics class that some of you might be enrolled at the same time as this class. So everything that describes the kinetics and the kinematics of motion of materials that are subjected to some forces and that tend to move due to those forces, this is what you described in the dynamics class. The dynamics class will explore what is the relationship between the force and the moment that you apply to solids and the motion that they will exhibit as a consequence of those forces. So this is not something that we are going to talk about in this class. What we are going to talk about in this class is the last type of behavior that material can exhibit when they are subjected to forces, which is that those materials can be deformed. So materials can exhibit some deformation when subjected to external forces. And this is what we are going to talk about in this class. We are going to talk about the deformation of materials once they are subjected to some external forces or external moment. So the second thing to define is, how do we define what is a deformation? So what is deformable? What does it mean to be deformable? And in this case, the way we are going to define a deformation or deformable materials, that's the material that can change either its volume or its shape. So those are the two types of deformation that we can have. Either a change in volume. This is, for example, if you apply a hydrostatic pressure on a given material, this material is typically going to shrink. So that's going to be a change in volume. And the other types of deformation that you can have is simply a change in the shape of this material. So for example, if you apply a shear deformation like this materials can change its shape without necessarily changing its volume. So the deformation of the materials can be either a change in volume, an elongation, a shrinkage, or a change in shape. So what we are going to talk about in CE 108 is primarily two different things, two different consequences of external forces that are applied to materials. So in this case, what we are going to talk about is, once you have some external forces or some external moments that are applied to a given solid, the first thing that this force will induce, this external force will induce, is that it will generate some internal load or some stress within the materials. So you have a given materials, you apply, for example, a three-point bending external forces like this. Those are the external forces that are applied by an external agent, applied by something else outside of the material. Those forces are going to result into some internal forces within the material itself. It's going to result into some internal load. So that is the first thing that is going to be a consequence of the external forces. You're going to have some external loads that are going to form within the material. Another way to describe this, which we are going to talk about in the next chapter, is that there is going to be the formation of some stress, some internal stress within the materials. And because of this stress, at some point there is a risk that the material might break. If the stress becomes too high, there is going to be a risk of fracture. So that's going to be the first thing that we are going to talk about in this class, is if you have an external forces, how does it induce an internal load, or can we find the relationship between the external forces that are applied by a material to the internal loads that are going to be forming inside this material? And if we can predict the internal load that forms inside the material and the internal stress that forms within the materials as a function of the external forces, then we can predict how likely this material is going to break. What is going to be the risk of fracture? The material is going to break if the stress that is forming within these materials exceed the strength of the material. So we're going to re-talk about this, but this is going to be an important thing. Understand the relationship between external forces and internal stress, and this is what is going to be useful to predict whether this material is going to break or not. So this is going to be about the risk of fracture. the second thing that we are going to talk about is not simply the internal load and the internal stress, but also the other thing that a material can do, even if it doesn't break, it's that these materials can be deformed. So we are going to talk about the internal deformation that a material can exhibit once it is subjected to some external forces. So again, in this case, we want to find the relationship between some external forces, the external forces or the external moments that are applied to these materials, and the internal deformation that occurs inside the materials. So basically what we want to find is that we want to understand the relationship between the causes of the deformation, which are the external forces. This is what is going to cause the deformation of materials. And we want to find the relationship between this cause and the consequence, which is going to be the response of the materials. And there's going to be two types of response that we are going to be interested in. Is first the deformation of the materials. Is this material is going to be deflected, for example, or elongated or shrinked, or what is going to be the internal stress, which is going to tell us if this material is going to break or not. So this is going to be really what we are going to do primarily during this entire quarter. The goal of this class is to find the relationship or the link, to find the relationship between the external forces that are applied to materials and the internal behavior of these materials. Internal load first, which is going to tell us if the material breaks or not, and the internal deformation, which is going to tell us if this material is going to be deflected or not, or how much deformation is it going to exhibit. And we want to find this relationship between the external things that are applied on these materials, which are the external forces and external moment, and the internal behavior of these materials. What we are going to do is that we are going to explore this relationship between external forces and internal deformation or internal stress for different types of deformation, materials that are subjected to axial load, that are elongated or shrink due to an axial load, or materials that are subjected to some torsion, materials that are subjected to some deflection, etc. So we are going to consider different types of potential deformation, and for each of those types we will want to derive some relationship that link the external forces that are applied to the internal behavior of the materials. And once we know this relationship, we can use it for different things. First, we can use it to predict what will be the deformation of a materials if we know the external forces that are applied. For example, if you have a bridge, and if you expect a given load that is going to be applied on this bridge, then you can predict how much deflection this bridge is going to exhibit. Or you can go the other way around. If you have a maximum deflection that you are willing to tolerate for your bridge, then you can back calculate what is the maximum force that this bridge can undergo. In the very same way, if you know what is the maximum stress that a given material can undergo before it breaks, then you can back calculate what is the maximum external force or the maximum external moment that you can apply to a material before it breaks. So you can either use, once you know the relationship between external forces and internal behavior, you can either predict the internal behavior of materials, or you can go the other way around, and if you have a given types of behavior, a given maximum deformation, or if you want to ensure that the material doesn't break, then you can back calculate what is the maximum force that you can apply or the maximum moment that you can apply to a structure before it has a risk of breaking. So what we're saying is that if you apply some external forces or some external moment on material, this material is going to be deformed. So there is different types of deformation that material can exhibit, and we are going to talk about only some of them in this class. So the first thing that material can do when they are subjected to some forces, the first way that they can be deformed is to show some elastic deformation. So just like a spring, if you apply a force, it will exhibit an elongation, and this elongation is proportional to the force that you apply. In this case, that is an elastic deformation. That is the first type of deformation. So for example, if you take a member like this, you apply a given lateral force to this member is going to be deformed like this. And typically in this case, the deformation, in this case the deflection, will be proportional to the force that you apply. And a key characteristic of elastic deformation as compared to other types of deformation that are not elastic is that elastic deformation are reversible. So in the case of elastic deformation, the way we can define those elastic deformation is that they are reversible, which means that now if you remove the load, the material will go back to its initial shape. It will go back to its initial volume and its initial shape, the same as the one that it had before the deformation was applied. So this is the key aspect of elastic deformation. They are reversible. And if you think about what dictates the elastic deformation of materials, if you have certain materials for the same force, certain materials will be deformed a lot, certain materials will be deformed only very little, right? So if you take a piece of rubber and you apply a given force, this rubber will be very largely elongated. But now if you apply the same force to a metal, then this metal will not be deformed in a very significant fashion. So the property that governs the propensity for materials to exhibit elastic deformation is the stiffness. So if a material is very stiff, then it will exhibit very little elastic deformation. And if a material is not stiff, then it will tend to exhibit a lot of elastic deformation. So the stiffness, which can be characterized and quantified by either the Young's modulus or the shear modulus, depending on if you characterize the stiffness of materials when subjected to actual load or transverse load. So those moduli will characterize how stiff the material is. So we are going to talk about this again in a few chapters when we are going to talk about the mechanical properties of materials. But the first thing to remember is that what characterizes how much elastic deformation a material can exhibit is governed by its stiffness. The second behavior that material can exhibit if they are subjected to some external forces, another type of deformation, is that those material can break. They can exhibit some fracture. So now we are talking about the case where you have a given member like this. You apply a given force to this material, and this material starts to break. So what does it mean to break? It means that you have a crack that starts to propagate, and eventually this material becomes made of two pieces. You used to have one single material, and now it becomes two pieces, so which means that it has broken into two pieces. So this is the definition of a fracture. You have created some new surface. So now, as a result of the fracture, you have some new surface that has been created. This new exposed surface that used to be inside the material is now exposed to the outside. So you have some new surface that has been created. So in this case, the deformation that is a consequence of fracture, in this case, it's not reversible. So you cannot simply put back the material like this and hope that the material will become cohesive again. So you would need to glue the material back, for example. So fracture is a non-reversible process. And if you think about what is the key property of a material that dictates whether it is very likely or not to break under a given load, the property of interest in this case is not the stiffness. The stiffness doesn't tell you if a material is very likely to break or not. In this case, the two things that will govern how likely materials are to break would be the strength first. So the strength tells you what is the maximum stress that the material can exhibit before breaking. And another thing would be the toughness or the fracture energy, which tells you how much energy or how much stress concentration, in the case of the toughness, the material is able to absorb before breaking. So in this case, we are going to mostly talk about the strength in this class. So the strength and how strong a material is characterize what is the risk, how likely a material is likely to break when subjected to some external forces. Then the third type of deformation that can occur in a material are some plastic deformation. So that's another type of potential deformation that a material can break in this case. So you consider still the same member. You apply a given force to this member, and this member is going to be deformed. But in the case of a plastic deformation, so the material does not break, so this is not a fracture, but it's in this case, it differs from the elastic deformation because the plastic deformation is irreversible. So that's the key aspect of a plastic deformation, is that unlike the elastic deformation, a plastic deformation is irreversible. Once you apply the load, the material is deformed, and once you remove the load, the material remains permanently deformed. It doesn't go back to its initial shape or doesn't go back to its initial volume. So in this case, the key property that will govern the propensity for a material to be deformed plastically or not is going to be first the yield stress. The yield stress is the minimum stress that you need to apply to a materials to induce some plastic irreversible deformation. Or another potential property is the hardness, which characterizes how resistant a material is to plastic deformation. If a material is very hard, then it's very resistant to plastic deformation. And then the last type of deformation are viscous deformation. So, though in this case, the key aspect of the viscous deformation, an example of deformation that is viscous would be the creep of deformation. In that case, the key aspect is that it's a time-dependent deformation. So far, the other deformation that we have considered, the elastic deformation, the fracture, or the plastic deformation, those are some deformation that occurs either instantly, or at least very fast. Now, if you consider viscous deformation like creep, now you consider a member like this, where you start to apply a given load, and if you wait long enough, then at constant load, this material is going to be deformed more and more. So this is what can happen, for example, if you take a bridge and if you apply a sustained load on this bridge potentially can start to creep over time. So in this case, this is something that can occur over months or potentially even over years. That's a deformation that is at a constant load. You apply a constant load, but if you just wait, you will have a time-dependent deformation where at constant load, the member will start to be deformed more and more due to creep deformation or due to viscous deformation. So in that case, the key aspect of these types of deformation is that it is time dependent. It occurs at under sustained load, at constant load, and it depends on time. It depends on the time that you are subjected the material to this load. And in this case, the key property that governs the resistance to material to these types of viscous deformation would be, for example, the creep compliance, which dictates how resistant to creep a given material is when it is subjected to a constant load. So what we are going to talk about mostly in this class are primarily the first two types of deformation. So either the elastic deformation and the fracture. We want to predict how likely a material is going to break, and if it breaks, in which direction is it going to break. And we want to predict the elastic deformation that the material can exhibit when subjected to some external load. Those are going to be the two things that we are going to focus in this class. One thing to note here is that there is different types of properties. So there is the stiffness, which characterizes how stiff a material is. There is the strength, which characterizes how strong a material is. There is the hardness, which characterizes how hard a material is. So all of those things, in the common language, if you think about something and you say it's very stiff or very strong or very hard, in many cases, we use those terms indifferentially. We use those terms as being as synonyms as possible. But in the fields of mechanics, those terms denote different things, right? So if you say about a material that is very stiff, it means that this material is very resistant to elastic deformation. It doesn't tell you anything about if this material is going to break or not. It doesn't tell you anything about the risk of plastic deformation. It's just telling you that this material is very resistant to elastic deformation, that it doesn't show significant elastic deformation. If you are talking about a material and you say it's a strong material, it doesn't tell you anything about the elastic deformation. It's only telling you that this material can sustain very high stress before breaking. So it tells you that this material is not likely to break. So that's what a strong material is. It's resistant to fracture. And if you're talking about a hard material, then it's a material that is resistant to plastic deformation. But again, it doesn't tell you anything about the elastic deformation or the fracture. And in many cases, in several cases, actually a material that is very hard typically has is not very tough, or a material that is very tough typically is not very hard. So those properties, first, they don't have to be correlated to each other, but in certain cases, they might actually be anti-correlated, where, for example, the toughness and the hardness tend to compete with each other. If you have something that is very hard, it's very unlikely to be also very tough. So usually you have some balance between different types of mechanical properties. So when you talk about the mechanical properties of different materials, it's important to use the right term and to not use indifferentially stiff, strong, and hard. So depending on the forces that are applied to a material and the direction of those forces, and depending on whether moments are applied or not to a given material, a material can be deformed in several fashion in different ways. Certain types of deformation will change the volume of the materials, while some other deformation will simply change the shape of the materials. So in this class, we are going to talk about primarily three types of deformation, three different types of geometrical deformation. The first one will be the actual deformation. So in this case, we will be talking about what happens if you take a given material and you apply an actual load like this. In this case, you will have an elongation of this materials, or you can potentially have a compression like this, and in this case you will have a shrinkage of this member. So that's the first thing that we are going to talk about. This is what happens when you apply a load that is axial along the longitudinal axis of the materials. The second type of deformation that we are going to talk about is what happens when you apply a torsion. So if you take a given material like this and you apply some moments like this to twist the material. So now in this case, if you apply a torsion, you will apply some external moment, and the result, the outcome, the consequence or the response of the material will be to be twisted. So that's going to be the second type of deformation that we are going to talk about. And then the last type of deformation that we are going to talk about are the deflection or the bending of the materials. So in this case, there is two main ways you can deflect a member. Either you will apply, for example, some lateral force like this, which will tend to deflect a material like this, or another way is to apply some moment like this, which will also tend to make a material that used to be straight will tend to make this material curved. So that's another types of deflection. So that's what we are going to talk about in the bending chapter. And for all of those chapters, it's going to be following a pretty common organization, where we will want to understand what is the relationship between the cause of the deformation, that is to say the external forces or the external moments that are applied to this member. So that's going to be the cause, and we will want to understand how this cause is going to induce some stress, and what is going to be the value of the internal stress within the material as a function of the external forces that are applied. This is what is going to tell us what is the risk of fracture of the material. Is this material going to break or not? And the second thing is we will want some mathematical relationship that can relate the cause, the external forces, to the deformation itself. So this is what we are going to talk about in the following chapter. But the way to characterize the deformation is the strain. And in this case, it's going to tell us how deformed the material is, how deflected, how twisted, or how elongated, or how twisted, how shrinked the material is. So this is going to be about the deformation. And in this case, in these two cases, in the case of stress and in the case of deformation, we will want to derive some relationship that relates the cause to the consequence. So the external forces to the internal stress, or to the internal strain, the internal deformation. So that's what we are going to see in this class. So the first thing before all of this that we are going to see in the next chapter is that we are going to review the key concept of statics that you need to remember to solve deformation problems. So that's what we are going to see in the next video.